The Arctic is one of the harshest environments on Earth. Temperatures can plunge to -70 degrees Fahrenheit. Winds howl across the ice at speeds that would knock a grown man off his feet. The sun disappears for months at a time, leaving nothing but endless darkness and cold that seeps into everything it touches. This is a place where survival seems impossible, where the very air can freeze the moisture in your lungs, where exposed skin dies in minutes. Yet in this frozen wasteland, one creature not only survives but thrives. The polar bear walks across the ice as if it were a pleasant spring day, swims through waters that would kill a human in seconds, and raises its young in temperatures that would turn most mammals into frozen statues. How do they do it? How does an animal weighing up to 1,500 pounds maintain its body heat in conditions that defy imagination? The answer lies in one of nature's most sophisticated survival systems, a combination of anatomy, physiology, and behavior so perfectly adapted to extreme cold that scientists are still discovering new details about how it works. If you are subscribed and you have liked this video, we are diving into the science. The polar bear, known scientifically as Ursus maritimus, meaning maritime bear, is the largest land carnivore on Earth. Males can reach lengths of 10 feet and weights of 1,500 pounds or more. Females are smaller, typically weighing between 300 and 700 pounds, but they are no less impressive in their adaptations to the Arctic environment. These bears have evolved over hundreds of thousands of years to become perfectly suited to life in one of the most extreme climates imaginable. Every aspect of their biology, from the structure of their fur to the chemistry of their blood, has been shaped by the relentless cold of their habitat. Understanding how polar bears stay warm requires looking at multiple systems working together in harmony, each one contributing to the overall ability to maintain body temperature in conditions that would be lethal to most other mammals. The most obvious and perhaps most important adaptation is the polar bear's fur. But calling it simply fur is like calling a supercomputer simply a calculator. The polar bear's coat is a marvel of biological engineering, a two-layer system that provides insulation so effective it has inspired the design of human cold weather gear and thermal materials. The outer layer consists of what are called guard hairs, long hollow shafts that can reach lengths of up to 6 inches. These are not ordinary hairs. Each one is a transparent tube, completely colorless despite appearing white to our eyes. This transparency is crucial to their function. The hollow structure serves two purposes. First, it traps air, and air is one of the best insulators known to science. The tiny air pockets within each hair create a barrier that prevents heat from escaping the bear's body. Second, the hollow tubes allow light to pass through them. This light travels down the hair shaft and reaches the bear's black skin underneath, where it is absorbed and converted to heat. This is essentially a biological solar panel system, harnessing the weak Arctic sunlight to generate warmth. The guard hairs are also coated with oil, making them water repellent. When a polar bear emerges from the frigid Arctic waters, it can shake itself dry almost instantly, preventing the water from freezing on its coat and creating a layer of ice that would drain body heat. Beneath the guard hairs lies the second layer of the fur system, a dense undercoat of shorter, softer fur that provides additional insulation. This undercoat is so thick that it creates an almost impenetrable barrier against cold air and water. The density is remarkable, with thousands of hairs per square inch creating a mat so tight that even hurricane force winds cannot penetrate it. This undercoat works in conjunction with the guard hairs to create multiple layers of trapped air, each one acting as an additional barrier against heat loss. The combination of these two fur layers is so effective that polar bears can actually overheat if they exert themselves too much, even in sub-zero temperatures. Scientists have observed polar bears taking frequent breaks during periods of activity, spreading themselves flat on the ice or snow to dissipate excess heat. This is a problem most Arctic animals would envy. The challenge of staying cool rather than staying warm, but fur alone, no matter how sophisticated, would not be enough to keep a polar bear warm in the Arctic. The next critical adaptation lies beneath the skin in the form of a thick layer of blubber, adipose tissue that can be up to 4.5 inches thick. This subcutaneous fat layer serves multiple purposes. Most obviously, it provides insulation, creating another barrier between the bear's vital organs and the killing cold of the environment. Fat is an excellent insulator because it has low thermal conductivity, meaning heat moves through it very slowly. A 4-inch layer of blubber is like wearing a built-in wetsuit, one that cannot be removed or damaged. But the blubber does more than just insulate. It also serves as an energy reserve, crucial for survival during the Arctic winter when food can be scarce. Polar bears can go months without eating, living off their fat reserves while waiting for sea ice to form so they can hunt seals. This ability to store and efficiently use energy is another key adaptation to their harsh environment. The blubber layer also provides buoyancy, helping polar bears swim more efficiently in the frigid Arctic waters where they spend considerable time hunting for seals. The polar bear's skin adds another element to this thermal protection system. Unlike their fur, which appears white, polar bear skin is black. This dark pigmentation is not accidental. Black surfaces absorb heat more efficiently than light surfaces, a principle familiar to anyone who has worn a black shirt on a sunny day. The polar bear's black skin absorbs whatever solar radiation manages to penetrate through the transparent guard hairs, converting light energy into heat energy. In the Arctic summer, when the sun never sets, this can provide a significant boost to the bear's thermal budget. Even in winter, when sunlight is scarce, every bit of absorbed radiation helps. The skin is also quite thick compared to other bear species, providing another layer of protection and insulation. The thickness helps prevent heat loss through radiation, the process by which warm objects emit infrared energy into their surroundings. The circulatory system of polar bears includes several remarkable adaptations for heat conservation. One of the most important is countercurrent heat exchange, a system found in the bear's limbs that prevents heat loss to the environment. Here is how it works. Arteries carrying warm blood from the core of the body to the extremities run parallel to veins carrying cooler blood back from the paws to the core. The warm arterial blood transfers heat to the cooler venous blood through the vessel walls, pre-warming the returning blood and pre-cooling the outgoing blood. This means that by the time arterial blood reaches the paws, it has already lost much of its heat to the venous system, so less heat is lost to the environment. Meanwhile, the venous blood returning to the core has been warmed up, reducing the energy needed to reheat it. This countercurrent exchange system is incredibly efficient, allowing polar bears to maintain a warm core temperature while keeping their paws at temperatures much closer to the ambient environment. Without this system, the massive surface area of their paws would act as radiators, constantly draining heat from the body. The paws themselves are another marvel of Arctic adaptation. Each foot is roughly 12 inches across, creating natural snowshoes that distribute the bear's weight and prevent it from breaking through thin ice or sinking into snow. The bottom of each paw is covered with small bumps called papillae, which provide traction on slippery ice surfaces. Between the papillae and toes, thick fur grows, adding insulation and further improving grip. This fur also prevents snow from balling up between the toes, which could impair movement and increase the risk of frostbite. The claws are thick, curved, and extremely sharp, perfect for gripping ice and catching seals. But even the claws play a role in temperature regulation. They are made of keratin, the same protein found in human fingernails, and keratin has relatively low thermal conductivity. This means the claws do not conduct heat away from the body as quickly as metal or bone would. Every detail of the polar bear's anatomy, down to the material composition of its claws, contributes to its ability to survive in extreme cold. The bear's body shape and size also contribute significantly to heat retention. Polar bears have a relatively compact body structure with small ears and a short tail compared to other bear species. This body plan minimizes surface area relative to volume, and since heat is lost through surfaces, reducing surface area reduces heat loss. This principle is known as Allen's rule in biology, the observation that animals adapted to cold climates tend to have shorter appendages than their warm climate relatives. Compare a polar bear to a sun bear from Southeast Asia, and you will see this principle in action. The sun bear has much larger ears and a longer snout, features that help dissipate heat in a tropical environment. The polar bear has done the opposite, tucking everything in tight to conserve every possible unit of heat. The large body size itself is also advantageous. Larger animals have a lower surface area to volume ratio than smaller animals. A 15-pound per pound polar bear loses heat much more slowly than a 15-pound Arctic fox, simply because it has proportionally less surface area through which heat can escape. The respiratory system of polar bears includes adaptations that prevent heat loss through breathing. In most mammals, breathing is a significant source of heat loss, especially in cold environments. Every breath exhaled carries warm, moist air out of the body and brings cold, dry air in. Polar bears have evolved an efficient system for recovering much of this lost heat and moisture. The nasal passages are long and convoluted, with a large surface area of mucous membranes. As the bear exhales, warm, moist air passes over these membranes, which are cooler than the air. Moisture condenses on the membranes, releasing its latent heat and warming the tissue. When the bear inhales, cold, dry air passes over these now warmed membranes, getting heated and humidified before it reaches the lungs. This countercurrent exchange in the respiratory system is similar to the system in the limbs, recycling heat that would otherwise be lost. Studies have shown that polar bears can recover up to 70% of the heat and moisture in exhaled air, a remarkable efficiency that significantly reduces the metabolic cost of maintaining body temperature. The metabolism of polar bears is another key factor in their ability to withstand extreme cold. Metabolism is the process by which the body converts food into energy, and in doing so, it generates heat as a byproduct. Polar bears have a relatively high metabolic rate compared to other bear species, partly because maintaining body temperature in the Arctic requires constant energy input. But they also have the ability to adjust their metabolic rate based on conditions and food availability. When food is plentiful, they can ramp up their metabolism and build fat reserves. When food is scarce, they can slow their metabolism to conserve energy, entering a state similar to hibernation without the deep sleep that characterizes true hibernation in other bear species. Pregnant females take this a step further, digging dens in the snow where they give birth during the winter months. While in the den, their metabolism slows dramatically, and they live off their fat reserves while nursing their cubs. This ability to modulate metabolism is crucial for survival in an environment where food availability varies dramatically by season. The diet of polar bears is almost exclusively carnivorous, focused primarily on seals. This high-fat diet is essential for their survival strategy. Seal blubber is incredibly energy-dense, providing the massive caloric input needed to maintain body temperature and build fat reserves. A single-ringed seal can provide enough calories to sustain a polar bear for several days. The bears are patient hunters, waiting beside seal breathing holes in the ice for hours or even days until a seal surfaces. When one does, the bear uses its powerful forepaws to grab the seal and haul it onto the ice. The preference for blubber and skin, the fattiest parts of the seal, is not just about taste. It is about maximizing energy intake while minimizing the metabolic cost of digestion. Proteins require more energy to digest than fats, and in a cold environment, every calorie counts. By focusing on the highest energy components of their prey, polar bears optimize their energy budget. Behavioral adaptations complement these physical and physiological features. Polar bears are not active all the time. They are strategic about when and how they exert energy. During the coldest periods or when food is scarce, they may spend long hours lying still, conserving energy and minimizing heat loss. They dig temporary daybeds in the snow, creating sheltered spaces that protect them from wind and further reduce heat loss. Wind chill is a significant factor in the Arctic. Still air is a decent insulator, but moving air strips away the warm boundary layer near the skin and dramatically increases heat loss. By creating windbreaks and shelters, polar bears reduce the effective temperature they are exposed to. They are also known to cover their black noses with their paws while sleeping, reducing heat loss from this small but exposed surface. These behavioral patterns demonstrate that polar bears are not just passively protected by their physical adaptations. They actively manage their thermal environment through learned and instinctive behaviors. The reproductive strategy of polar bears is also intimately tied to their thermal adaptations. Females typically breed in the spring, but the fertilized eggs do not implant immediately. Instead, they undergo delayed implantation, floating freely in the uterus for several months. This allows the female to time the actual pregnancy so that birth occurs in the middle of winter when she is safely in her maternity den. The den itself is an engineering marvel, excavated in deep snowdrifts or sometimes in frozen soil. Snow is an excellent insulator, and the den maintains a temperature significantly warmer than the outside environment, sometimes as high as 40 degrees warmer. The mother gives birth to typically 2 cubs, each weighing only about 1 pound and covered in fine hair but with eyes closed and no real ability to regulate their own body temperature. For the first few months of life, the cubs are entirely dependent on their mother's body heat and the insulation provided by the den. The mother does not eat during this time, living entirely off her fat reserves while producing rich milk to feed her growing cubs. By the time they emerge from the den in spring, the cubs have grown to about 20 pounds and are beginning to develop their own insulating fur and fat layers. The development of thermal regulation in polar bear cubs is a gradual process that mirrors their overall maturation. Newborn cubs cannot shiver effectively, one of the primary mechanisms mammals use to generate heat. Instead, they have brown adipose tissue, also known as brown fat, which generates heat through a process called non-shivering thermogenesis. Brown fat is packed with mitochondria, the cellular structures that produce energy, and contains a special protein that allows these mitochondria to generate heat directly rather than storing energy as ADP. This is particularly important for newborns, who have a high surface area to volume ratio and would lose heat rapidly without this mechanism. As the cubs grow, they gradually develop the full suite of adult thermal adaptations. Their guard hairs grow longer, their undercoat becomes denser, their blubber layer thickens, and their ability to regulate blood flow to the extremities improves. By their second winter, they have most of the physical adaptations of adults, though they still have much to learn about the behavioral aspects of staying warm and finding food in the harsh Arctic environment. Scientists studying polar bears have discovered that their thermal adaptations are so effective that the bears are almost invisible to infrared cameras, the devices that detect heat radiation. When researchers tried to study polar bear populations using infrared imaging from aircraft, they found that the bears barely showed up against the cold background. This is because almost no heat escapes through their fur. The hollow guard hairs and dense undercoat trap virtually all body heat, and what little does escape is so diffuse that it does not create a detectable infrared signature. Only the bear's breath and occasionally their nose and eyes show up on infrared. This remarkable level of insulation led engineers and materials scientists to study polar bear fur in hopes of developing better thermal materials for human use. While we cannot exactly replicate the biological system, understanding the principles behind it has informed the design of everything from winter clothing to building insulation materials. The habitat of polar bears is changing rapidly due to climate change, and this presents new challenges for their thermal adaptations. Polar bears are superbly adapted to cold, but they are not particularly well adapted to warmth. As Arctic temperatures rise and sea ice declines, polar bears face longer periods on land where they cannot hunt effectively. This forces them to rely on their fat reserves for extended times, and without access to seals, they cannot replenish these reserves. The loss of sea ice also means more time spent in water, which, while polar bears are excellent swimmers, is energetically expensive. Swimming uses more calories than walking, and in warming waters with longer distances between ice flows, bears burn through their energy reserves faster. There are also observations of polar bears experiencing heat stress during unusually warm periods, a problem they are not well equipped to handle. Unlike overheating in winter, which they can manage by spreading out on snow, dealing with genuinely warm temperatures is difficult for an animal wrapped in what amounts to a super-insulated survival suit they cannot remove. The relationship between polar bears and their prey species is also affected by thermal factors. Seals, particularly ringed seals and bearded seals, are the primary food source for polar bears. These seals also have impressive adaptations to Arctic conditions, including thick blubber layers and the ability to survive in frigid waters. They give birth and nurse their pups on sea ice, using breathing holes and snow dens for protection. Polar bears hunt seals most effectively when there is stable sea ice, which provides a platform for hunting and allows seals to maintain their breathing holes and dens. The formation and breakup of sea ice is driven by temperature, and as Arctic temperatures rise, the sea ice season is becoming shorter and less predictable. This affects both seals and bears, disrupting the carefully balanced ecosystem that has existed for thousands of years. The timing of ice formation and breakup can determine whether female bears have enough time to build fat reserves before denning, whether cubs survive their first year, and whether the bear population as a whole can sustain itself. Historical observations of polar bears reveal that their range and behavior have changed over time, but their fundamental thermal adaptations have remained constant. Polar bears evolved from brown bears sometime between 350,000 and 600,000 years ago, relatively recently in evolutionary terms. Genetic studies suggest that an isolated population of brown bears became trapped in an increasingly cold environment and over many generations developed the specialized features we see in modern polar bears. The earliest known polar bear fossils show that even at that early stage, they had already developed many of their key adaptations, including enlarged paws, modified teeth suitable for a carnivorous diet, and presumably the beginning of their advanced fur structure. The speed of this evolution suggests strong selective pressure, environments so extreme that only the most well-adapted individuals survive to reproduce. This evolutionary history is important for understanding the future of polar bears. They adapted to increasing cold over hundreds of thousands of years, but now they face rapidly warming conditions occurring over just a few decades, far too fast for evolutionary adaptation to keep pace. The cultural significance of polar bears to Arctic indigenous peoples reflects deep understanding of the bear's adaptations and behaviors. Communities that have lived alongside polar bears for thousands of years develop detailed knowledge of how these animals survive and thrive in conditions that challenge human survival. Traditional hunting practices respected the bear's abilities, and various taboos and practices governed interactions with polar bears. Stories and teachings passed down through generations contained practical information about polar bear behavior, often framed in cultural or spiritual terms. Modern scientific understanding of polar bear thermal regulation confirms much of what indigenous knowledge has long recognized, that these are animals perfectly suited to their environment through a complex interplay of physical adaptations and learned behaviors. The partnership between indigenous knowledge holders and scientists has enriched our understanding of polar bears and contributed to more effective conservation strategies. Research methods for studying polar bear thermal regulation have evolved significantly over the decades. Early studies relied primarily on examination of harvested bears and observations of captive animals. Modern techniques include remote cameras, satellite tracking collars, hair and tissue sampling for genetic analysis, and sophisticated thermal modeling. Scientists can now track individual bears across vast distances, monitor their activity patterns, and even estimate their body condition and energy balance through mathematical models. These tools have revealed details about polar bear biology that would have been impossible to discover through direct observation alone. For example, satellite tracking showed that some polar bears make extraordinary long-distance swims of over 400 miles across open water, a feat that requires maintaining body temperature in near-freezing water for days at a time. Analysis of these journeys has provided insights into the limits of polar bear endurance and the energy costs of different activities. The comparison between polar bears and other Arctic mammals highlights the multiple solutions evolution has found to the problem of cold. Arctic foxes survive using different strategies, including seasonal changes in fur density and color, smaller body size that allows them to den in snow more easily, and a more omnivorous diet that gives them access to a wider range of food sources. Musk oxen rely on an incredibly thick coat of fur, social behavior that sees them grouping tightly together for warmth, and the ability to survive on sparse vegetation during the winter months. Seals combine blubber insulation with the ability to remain underwater where temperatures are more stable, only coming up briefly to breathe. Each species has found its own solution, but the polar bear's combination of size, carnivorous diet, marine hunting strategy, and multi-layered insulation system is unique among Arctic mammals. Understanding these different strategies helps scientists appreciate the complexity of Arctic ecosystems and the specialized nature of each species' adaptations. The future of polar bears depends on whether their thermal adaptations, so effective against cold, can help them survive in a warming Arctic. Some scientists suggest that polar bears might adapt by spending more time on land and shifting to different food sources, perhaps hunting terrestrial prey or scavenging. However, their physiology is so specialized for a marine diet of high-fat seals that it is unclear whether they can successfully make such a transition. Other research suggests that some subpopulations might persist in areas where sea ice remains more stable, while populations in southern regions of their range may disappear. There is also the possibility of genetic adaptation over time, but this requires both genetic variation within the population and enough time for natural selection to work, neither of which is guaranteed. The polar bear's remarkable thermal adaptations allowed it to colonize one of Earth's most extreme environments, but those same adaptations may limit its flexibility in responding to rapid environmental change. Conservation efforts for polar bears must take into account their thermal biology and its relationship to sea ice habitat. Protecting polar bears means protecting the Arctic marine ecosystem, including the sea ice that serves as their hunting platform and the seal populations they depend on. This requires addressing climate change at a global scale, reducing greenhouse gas emissions, and slowing the rate of Arctic warming. It also means protecting denning habitat, managing human-bear interactions in ways that minimize conflict, and continuing research to monitor population health and trends. The thermal adaptations that make polar bears such effective Arctic predators also make them particularly vulnerable to the loss of cold habitat. They cannot simply move north as temperatures warm because they are already at the top of the world. and they cannot adapt to warmer conditions without losing the very features that define them as polar bears. Their fate is inextricably linked to the future of Arctic ice and the global climate system that determines its extent and duration. The study of polar bear thermal regulation has applications beyond conservation biology. The principles discovered through this research inform human technology and medicine. The hollow structure of polar bear guard hairs has inspired the development of synthetic insulating materials with improved thermal properties. The countercurrent heat exchange system in their circulatory system has applications in designing more efficient heat exchangers for industrial processes. Understanding how polar bears manage their metabolism during extended fasting periods has implications for studying human metabolism and developing treatments for obesity and metabolic disorders. The way polar bear skin absorbs solar radiation has informed the design of solar collectors and passive heating systems. Nature has had millions of years to experiment with solutions to complex problems, and studying the results of that experimentation provides insights that can benefit human endeavors across multiple fields. The thermal adaptations of polar bears also raise interesting questions about limits and trade-offs in evolution. Being perfectly adapted to one environment often means being less adaptable to changes in that environment. The polar bear's extensive insulation system is wonderful in the Arctic but would be a severe disadvantage in a warmer climate. The specialized diet of high-fat seal meat provides optimal nutrition for their lifestyle but leaves them vulnerable if seal populations decline or become inaccessible. The large body size that helps with heat retention also means higher absolute food requirements and longer fasting periods if hunting is unsuccessful. Evolution does not produce perfect organisms that can thrive anywhere. It produces organisms that are optimized for specific conditions, and when those conditions change too rapidly, even the most sophisticated adaptations may not be sufficient. The polar bear represents both the power and the limits of evolutionary adaptation, a species so specialized that it excels in its niche but struggles when that niche begins to disappear. Understanding how polar bears avoid freezing in the Arctic requires appreciating the integration of multiple systems working together. The fur provides insulation and captures solar energy. The blubber provides additional insulation and energy storage. The black skin absorbs heat. The circulatory system conserves warmth through countercurrent exchange. The respiratory system recycles heat from exhaled air. The metabolism generates heat efficiently and can be adjusted based on conditions. The body shape minimizes heat loss. The behavior patterns reduce unnecessary exposure. The diet provides optimal fuel. Each component is impressive on its own, but the true marvel is how they function as a unified system, each adaptation enhancing the effectiveness of the others. This kind of integrated complexity is common in nature but rarely appreciated until examined closely. It demonstrates that surviving in extreme environments is not about having one amazing adaptation, but about having many good adaptations that work together harmoniously. The polar bear stands as one of nature's supreme achievements in thermal engineering, a living testament to the power of evolutionary adaptation. In a place where temperatures can kill in minutes, where ice and water dominate the landscape, where winter darkness stretches for months, these massive carnivores not only survive but thrive. They hunt, they raise families, they sleep comfortably on frozen ice, and they swim through seas that would quickly kill most mammals. The answer to how they avoid freezing is not simple because the solution is not simple. It is a masterwork of biological engineering built over hundreds of thousands of years through countless small improvements and refinements. From the hollow tubes of their fur to the chemistry of their brown fat, from the curves of their claws to the structure of their blood vessels, every detail contributes to the whole. As the Arctic changes and polar bears face an uncertain future, understanding these adaptations becomes more than an academic exercise. It becomes a window into what we stand to lose if we cannot protect these remarkable animals and the frozen world they call home.